Hello and welcome to the resonance tutorial. For this tutorial, you should have the basic knowledge of resonance structures. This tutorial is meant to be a review of resonance structures. There are two very important rules to remember when drawing resonance structures. 1. Single bonds cannot be broken. And 2. The octet rule cannot be violated. During this tutorial, we will go through several examples together, and then I will have you practice by pausing and unpausing the video. Remember that resonance is not an equilibrium situation. The molecule does not go back and forth between resonance structures. Molecules, or ions, are averages of resonance structures. One way to think of this is to think of the liger, which is an average of a tiger and a lion. The liger has some of the characteristics of a lion and some of a tiger, but does not switch back and forth between them. A liger is itself all of the time, not a lion half of the time, and a tiger half of the time. We will use a benzene ring to help us understand resonance on a chemical level. In this example, we can see two resonance structures of the benzene ring, each with alternating carbon-carbon single and double bonds. Between these two resonance structures, we see a six-membered ring with a dashed circle in the center of the benzene ring. This structure is an average of the two resonance structures for benzene, where each of the carbon-carbon bonds is approximately 1.5 bonds, a mixture of a single and double bond. Our first example is this ion. Before we begin this example, we should label the oxygen atoms to make sure we are drawing a resonance structure and not the exact same molecule. So we will label this oxygen atom A and this oxygen atom B. In this molecule, we see oxygen atom A has a negative charge, and oxygen atom B is double bonded to the same carbon atom. This double bonded oxygen has a pair of electrons in the pi bond. When drawing resonance structures, we move pi and lone pair electrons around the molecule, taking care not to break single bonds or violate the octet rule. In this molecule, we can move a lone pair from the negatively charged oxygen atom A to become a double bond between that oxygen atom and the carbon atom. We want to make sure we follow the octet rule on the carbon atom, so the electrons in the pi bond between the oxygen atom and the carbon atom will transfer to oxygen atom B, therefore giving us the following resonance structure. Before we are done with this problem, we need to make sure there are no other options for any other resonance structures. Remembering we can move the pi electrons to draw resonance structures. However, the pi electrons must still be associated with one of the sp2 carbons in the original pi bond. The pi electrons could not move here because this would break the octet rule because the sp3 carbon would have 5 bonds. We could also not transfer a pair of lone electrons to create a double bond between the oxygen atom with the negative charge and the sp2 carbon, because this would also break the octet rule by bonding the sp2 carbon 5 times. We will work through one more example together. We see in this example, there are 2 lone pairs on this oxygen atom and a positive charge on the carbon atom next to it. This gives us a hint as to how to find a resonance structure for this molecule. If we are to transfer a lone pair from the oxygen atom to make a pi bond in between the oxygen atom and the carbon atom with a positive charge. This does not violate the octet rule for either the carbon or oxygen atoms. This is also the only resonance structure we can make without breaking that octet rule. So the resonance structure would look like this. If we were to draw the double bond forming between the oxygen atom and the methyl group, we would be breaking the octet rule because the carbon atom would have 5 bonds. And this is how that resonance structure would look. So as we can see in this resonance structure, this carbon atom has 5 bonds, therefore breaking the octet rule. Now I will have you work through an example on your own. When their structure appears on the screen, please pause the video, write down the structure and all of the possible resonance structures. Then play the video when you are done and we'll go through the answers. Here is the structure. Please draw all of the possible resonance structures for it. Please pause the video and good luck. Welcome back. Let's go over the answer. We can see the structure has a positively charged carbon atom and there is a carbon-carbon double bond in the molecule. We can move the pi electrons to draw resonance structures. However, the pi electrons must still be associated with one of the sp2 carbons in the original pi bond. This means we can draw a double bond here, which would result in the following resonance structure. Some of you may be tempted to try and move the double bond here, which results in the following structure. This does not work for 2 reasons. First, it violates the octet rule on the end carbon. Second, when moving pi electrons, these electrons must still be associated with one of the sp2 carbons that were in the original pi bond. Note, when we move the pi electrons, the carbon that only has 3 bonds to it is now this one. This means the carbon atom is sp2 hybridized and therefore has a positive charge. This is the only resonance structure we can draw without violating the octet rule or breaking single bonds. We will do another practice molecule. Again, pause the video, write down the structure of the molecule, draw all of the resonance structures for the molecule, and then play the video to check your answers. Here is the molecule. Please pause the video at this time and good luck. Hello again. In this molecule, we see 2 lone pairs on the oxygen atom and a double bond between that oxygen atom and the carbon atom it is bonded to. The electrons in the pi bond can move up to become a 3rd lone pair on the oxygen atom. This will give the oxygen atom a formal charge of -1 and the carbon atom a formal charge of +1. And this is the resonance structure. This is the only resonance structure we can draw for this molecule without breaking the octet rule. Why do you think the electrons go towards the oxygen rather than the carbon? Think about electronegativity. We have one more molecule for you to practice with. Again, please pause the video, write down the structure of the molecule, draw all of the resonance structures for that molecule, and then play the video to check your answers. Here is the ion. Please pause the video at this time, and good luck. Welcome back. Let's check your answers. To start off the problem, we can draw in all of the hydrogen atoms bonded to the carbon atoms in the ring and the substituent. We see a positively charged carbon atom in the substituent. We also see several carbon-carbon double bonds in the 6-membered ring. The electrons in the pi bonds are able to move, and therefore a resonance structure can be drawn by moving the electrons in the pi bond to make a pi bond on the substituent, and therefore the positive charge will move to the carbon on the ring. That would give us this resonance structure. This is only one of the possible resonance structures, but we need to draw all of the possible resonance structures. This means we can move the positive charge all the way around the ring because the other pi bonds in the ring. The next resonance structure would result from this pi bond moving over to create a carbon-carbon double bond next to it. which moves the placement of the positively charged carbon. So we can move the positive charge all the way around the ring, creating many other resonance structures. In determining whether or not you can draw resonance structures for a molecule or ion, you should look for the following patterns. Please note, these patterns have been illustrated by examples in this tutorial. Our first pattern is having a lone pair next to a pi bond. In the structure all the way on the right, this is representing that negative charge is shared between those atoms in the molecule. The second pattern is having a lone pair next to a positive charge. The third pattern is having a pi bond next to a positive charge. Again, the structure all the way on the right shows that positive charge is being shared between those atoms in the molecule. The fourth pattern is having a pi bond between two atoms, where one of those atoms is more electronegative than the other. The last pattern we saw was having pi bonds going all the way around the ring. Please remember our resonance analogy when thinking about these molecules. Think of the liger. The liger has some characteristics of a lion, some of a tiger, but does not switch back and forth between them. A liger is itself all of the time, not a lion half of the time, and not a tiger half of the time. Thank you so much for watching this tutorial, and please feel free to watch the other tutorials. Thank you again, and good luck.